Well, hello everyone, and welcome to our webinar today, Lightning Safety and Accident Protection. I'm your host, Greg Gocher, here in Phoenix, Arizona, and our webinar will be presented this afternoon by Peter Carpenter, Director of Applied Engineering, who's located at our corporate facilities in Boulder, Colorado. Peter's presentation today is a 30-minute subset of a more fully detailed technical presentation, which we've posted on the YouTube address you can see on this slide. With that, I'd like to introduce you all today to Peter Carpenter, Lightning Protection Expert.
Thanks, Greg. Well, appreciate all you taking the time to join us this afternoon. And as Greg mentioned, we'll have about a 30-minute discussion. I'm going to keep it at a pretty much a somewhat simple discussion on lightning and lightning protection. So obviously, as we mentioned, if you want a lot more minutia, detail, technical information, I suggest you do look at the YouTube video, which takes about an hour and 20 minutes, but does give you additional technical data that will kind of expand the discussion we're doing this afternoon. So with that said, we can go ahead and proceed to the first slide. Kind of the agenda for this afternoon. Again, I'm going to move rather quickly here because we do have about 30 slides to go through approximately. So we're going to do a little of a quick history of LEC, what some of our clients say on about LEC technology over the past 30-plus years, what our expertise, what we bring to the table as a company for lightning protection. We'll talk about safety and accident protection, and then we go into basically our technology that we use in preventing lightning collection, which we call the dissipation array system. And then, as I mentioned, we'll have hopefully some time at the end for answering any questions you may have. Quick history on LEC. We've been around since 1971. Our founder actually kind of came out of the Apollo projects as a reliability engineer for launch vehicles in Cape Canaveral. And when he looked through what could impair a Apollo mission reliability, obviously a lightning strike to the launch vehicle during a critical moment could cause a significant hazard to the actual launch itself, could scrub the mission, or could cause, worst case scenario, a catastrophic event. He did some research and found that really there's been no true lightning improvements as far as lightning protection from a direct strike standpoint since Ben Franklin. We have 14 patents right now, U.S. patents, 2 more under are pending. Over 70,000 system years of performance. Basically, we're saying all of our systems installed worldwide. Every year they achieve 1 year system performance. Actually, we've now exceeded 70,000, but we're at least at that benchmark. We have dozens of Fortune 100 clients. To say a few, FedEx, ExxonMobil, BASF, International Paper, Shell, almost every major chemical plant, refinery, we've worked with in one capacity or another. So I'm not going to really read all these comments, but I'll kind of highlight them for you. You can kind of see some of the testimonials we have here, whether it be from Federal Express. Again, you're going to get the slide presentation so you can spend some time looking at this yourself when you have time, but whether it be Federal Express, Memphis, a complete air hub there protected, Mobil Beaumont, ExxonMobil Beaumont, Texas, Telluride Gondola, Telluride, Colorado, Tri-State here, all have had very glowing things to say about our technology. Here's kind of maybe some more highlights. Mid-Carolina Electric, Liers, he estimated a few years after these systems were installed that they saved over $1 million in the losses since the installation, and that was only about 3 years after installation at Mid-Carolina Electric Co-op. This particular case here, with Chevron, the equipment has proven its value far beyond initial cost. A lot of times, obviously, you want to get, or we have the question, what's my return on investment? And our clients very quickly see that they can recoup that initial investment very quickly over the first couple, 3 years, and after that, it's just paying dividends as far as protection. Glen Waggle, basically, we have saved over $100,000 in the first year alone in losses due to lightning. So, again, just a few examples of a positive success with our clients due to our product's performance. Jack Barr at Turner Broadcast. One thing that I like to say, too, about our systems is not only do you get the initial protection of the downtime, the outages, but we also see a lot of our clients reducing their maintenance costs over time, where their maintenance cost goes down. They have less maintenance on electronics going out because they're getting more life expectancy out of their electronics. So what do we do at LEC? Well, we consider ourselves kind of a one-stop shopping when it comes to lightning protection. And when I say that, it means we have really 3 individual product lines that we integrate together in a systems approach. These product lines include lightning prevention products, whether it be our dissipation array system or our spline ball ionizers or spline ball terminals. We also have surge protection for AC power, low voltage signal lines, data line, coax line, control lines, and we also have enhanced grounding products to actually provide a good low impedance ground. I like to describe a systems approach in lightning protection as utilizing 3 legs of a stool. Those 3 legs being the direct strike protection, strategic surge protection on AC power, data line, control lines, and grounding products, all working together as a system, as a team, to provide this total isolation. We can always carve out 1 or 2 of those depending on the needs and concerns, but that's what we bring. We bring the expertise and the wealth of knowledge to integrate those into effective systems to protect a facility from a lightning-related outage. Well, talking about the initial evaluation of lightning protection going back to the Apollo project, what Roy Carpenter found out, the founder of the company, found out was that when he did his original evaluation for the Apollo project, the technology used to protect that launch vehicle, that rocket, if you will, had its roots in design in Benjamin Franklin. Ben Franklin is the father of the lightning rod. In fact, it's still called in many circles the Franklin system. So you think about this, of course, that goes back over 200, now approaching 250 years before this, since this technology was developed. And you think how we've evolved in our society with communications, power generation, space travel, air travel, but we're still using a lightning protection system that goes back to the 1700s. There has to be a better way of doing that, and that's what really kind of launched our founder on a new way of protecting against a lightning event. Now, the Franklin system, the lightning rod, the Franklin rod, really is designed as a strike termination point. It's designed to be the preferred collection point for a lightning strike. There are certain envelopes that go with that, how many lightning rods you need in a building, that all go into some of the standards I'll talk about in a minute. And it's really primary function of the lightning rod when Ben Franklin invented it was structural protection. Back in 1750, 1760, there was no computer systems. There was no entertainment center. There was no process control, logic systems, DCSs, instrumentation. So all they really cared about was protecting their home and their livestock from a fire caused by lightning. So today we use standards that really still have their roots in the Ben Franklin system. Here on this slide, we're showing you some of the more commonly used standards that we might see in the United States when it comes to lightning protection. The 2 that we see here in the United States typically would be the National Fire Protection Association 780, that's the red document there, or Underwriters Laboratory, UL, the blue document. But their primary mission is based for or founded on structural protection, personal safety, not geared to electronic integrity. And that's kind of their limitations. Where we want to go much beyond, well beyond structural integrity, personal safety, we also want to go into electronic integrity and protection. And that's really where these 2 standards don't address that. And really, again, they're attraction systems, by the way. The NFPA 780, 780, and the UL 96A standards are designed as lightning collectors. Their mission is to collect lightning to the lightning rod and not hit the building. But they are not 100%. They still can actually not collect every strike. In fact, if you see on this particular illustration, there is a wooden distribution pole, and you can barely see the lightning rod on the very top of that pole. It's kind of going outside the box. Well, the lightning strike actually missed that lightning rod and hit the pole beneath it because it actually hit a sliver of wood. So you're not always going to be assured that lightning will hit the preferred collection point. Let's talk briefly about lightning itself and how it really discharges. I'm not going to go into a lot of discussion about this because it takes a lot of time, and we don't really have a lot of time again this morning to go into all the minutiae that makes up a lightning cloud, a thunder cell, but it goes down to these base components: water, wind, temperature variation, frozen water, hail, gravity collision, electron collection. In my 1.5 hour presentation on YouTube, I encourage you to go to that, and it's about a 5-minute discussion just on that alone. These bullet points really impact what creates the charge in a cloud. So after we have had that recipe for a lightning strike developed, or thunder cell, electrical storm, lightning storm developed, we have a scenario illustrated here. So as you can see by the arrow, we have a thunder cell, and you'll see the positive charge. Positive charge is going to be at the upper portion of the cloud, and we're going to have a negative charge at the bottom portion of the cell. And you can see the arrow being kind of moved along the base of the cloud and that negative charge. The Earth and the Earth structure beneath that cell has a positive charge forced on it, induced on it. So here we're showing you the positive charge on the Earth that is forced, induced on the Earth surface and buildings, towers, trees, caused by the force and magnitude of the negative charge on the base of the cloud. Now, during a mature storm, and I don't want to get too technical here, I'm not sure how technical we are in the group here, but we have a very high electrostatic field charge in the air. And that's what we're talking about over there when you see the 5 to 30 kV per meter. That's how we express the charge. If we're going to have a lightning strike developed and in our area of concern, the charge per meter of air gap is going to be at least 5,000 volts per meter, possibly up to 30,000 volts per meter. Now, here again, we have the positive charge on the upper part of the cloud, negative on the base, and we force that positive charge on the Earth as well as on the structures. You can see we also have all the little structures, positive charge. Now, you'll see the 10 to the 8th volts there. What does that mean? Well, if we were to measure with a voltmeter from the Earth to the base of that cloud, we'd have the voltage potential of 10 to the 8th volts, about 1 billion volts. And granted now, why is that important? Well, when you have that much charge difference between the positive on the Earth and the negative charge on the base of the cloud, I think many of us have heard, opposites want to attract. And that's an electronic, really, definition. Positive and negative charges want to come together. They want to, as we say, short out. They want to meet. The reason that the positive and negative charges don't come together is the air between that negative charge, if you can point to the negative charge there on the cloud, and the positive charge on the Earth. What stops those two things from meeting, those two charges? It's the air. The air is a natural buffer. We call it an insulator, but only to a certain potential, certain level. When we get to the magnitude of around 10 to the 8th volts, 1 billion volts between the cloud and the Earth, the air can no longer work as a buffer. It starts to conduct. It allows that meeting effect. And so now, if you see the little lightning bolt right up there, there you go, that lightning bolt is now the initiation of that coming together of those two charges. So now we have a lightning bolt developed between the positive charge in the cloud and the negative charge on the Earth. And in simple terms, that's like a conductor coming down from the cloud, a wire. Well, now as we bring that lightning bolt from the cloud, and that cloud may be 10,000 feet above the Earth, it's coming down towards the Earth very quickly in less than a second, and as it gets close to the Earth, before it actually meets the Earth, before we actually even have that lightning bolt hit the Earth, we have what we like to call multiple upward streamers developed, also called counterleaders. These are little fingers, if you will, of negative potential leaping up off of the Earth and earthbound structures. So here you can see, 8 to 10 little upward counterleaders off a tower, off a vessel. We even show one on a blade of grass out there in the middle of the field right there. All of these are trying to what we like to describe as win the collection race. Why is that important? Because one of those counter leaders will actually reach up mid-air and make that electrical connection with that lightning bolt. Let's just say, that one right there next to the tower, that close one, it wins the race. So now what has happened? We have now determined that that little tower right there is going to be the one collecting the strike because it had the most competitive streamer that won the race and determined point of collection. To actually develop upward streamers, the charge in the air, and again, I don't want to get too technical, but I have to say this, it has to be around 100,000 volts per meter. Why is it so high? Because when that lightning bolt gets close to the earth, it actually will then increase the field intensity around that lightning bolt to actually up to and exceeding 100,000 volts per meter. And that's what then generates these upward streamers. So keep that in mind. So when I talk about how our technology works, you can understand what our goal and our method of operation is in protection. To have collection, you have to have streamer generation and streamer collection. If you don't have a streamer collect or generate, you'll never collect to your site. Keep that in mind for later in discussion. So here are some examples of a photograph really showing you multiple upward streamers. And you can see that they were all multiple in this particular one lightning strike. There was actually 5 visual upward streamers. There's a very pronounced one right there you can see that has the arrow on it. But the one you can't see is the one that made the collection. It actually closed that electrical circuit. Once you've made that collection, now you have what we call in an electronics term or an electrical term, a closed circuit. Once you have a closed circuit, all that energy in that electrical storm is going to funnel down that closed circuit and cause our damage. But here's an example of, yes, you can actually see. Your naked eye can't see it. You have to see it with a camera. You'll never see a streamer with your eye. Your eye can't react fast enough. But if you have a fast-acting camera, you can see it. Now, when we talk about trying to keep our facility protected, really reality is, in most cases, it's not the direct strike, it's the secondary effects, the byproduct of this strike. Now, again, I'm going to, because of time, I'm not going to go too deep in here. Again, I kind of going back to that YouTube video because you'll get more detail off that. But remember when I mentioned that during an electrical storm, there's a positive charge force on the earth. So if you go down there's a positive charge on the earth. In this particular example, we're showing you buried conduit conductors in the earth between the main control room right there and this remote process building. And those conduits have wires running between the field instruments and controls and back to the control room. Now, if we have a lightning strike to the tree, as you can see by the illustration, a lightning bolt hits the tree, all that positive charge, that's force on the earth, has to flow very quickly across the Earth's surface. You look at those yellow arrows. We're showing you that that positive charge now has to flow in microseconds, all less than 1 second, from the point of where it was forced on, induced by the cell, the cloud, to that point of termination. And as it flows across those cables, you're going to induce a surge. So you see a little squiggly line right there we're showing you right there? What we're trying to show or illustrate is that a voltage transient, a surge, has been induced on those low voltage cables. In fact, unfortunately, I can give you a real life experience where my neighbor's tree was hit about 2 months ago, about a 60-foot cottonwood tree, and unfortunately killed the tree, and then my irrigation low voltage circuit went out. So I lost all my low voltage circuits on my irrigation controls due to this exact phenomenon, what's called an earth current transient. I didn't have any of my building, my home was no problem as far as being struck. The tree actually was hit about 100 feet, well, close to 100 feet away, and had bark flying on my porch from that strike. So the area of influence is quite large from these secondary effects. You can also call it an atmosphere transient. I'm not going to go into a lot of detail here either. I just mentioned 5 or 10, 30,000 volts of charge in the air. When you have a lightning strike to that tree, that field collapses. And when that field collapses, it induces a voltage transient. And by doing so, we can create voltage impulses on overhead lines. And here's an example of now that voltage transient being induced on an overhead cable caused by an atmosphere transient. Again, a secondary effect. Our system really is kind of unique in the fact that we want to take a different approach. We want to take the opposite approach. Technically, we call it an inverse approach. Rather than trying to collect lightning like a lightning rod, we want to actually prevent collection. And this is the dissipation array system that was developed back in 1971. There's been some improvements over time, but the whole premise is prevention. Been around since 71. We have over a 99% success rate of preventing all potential strikes, over 70,000 system years, and we do offer a no-strike warranty on our technology. What that basically means, if your facility collected a strike, as long as under a recertification program, we upgrade the system at no cost to the client. And that's been the same warranty we've offered since 1971. So I'm going to take a hold about 5 minutes here and walk through this. How does our technology work versus the lightning rods? Lightning rods want to attract lightning, develop streamers. What we want to do and what we will do is prevent streamers. Now here we're showing you an example of a stack. On that stack, and I'll show you a photograph later on of a hemisphere array or stack array on a stack. But we call it an ionizer. We have the ionizer on the stack. Now in this particular application or illustration, we're only trying to protect the stack itself, the electronics on the stack, as well as the buildings beneath it. So these buildings right inside that circle are all in the envelope. The radius of protection is basically 1.25 times the height. Now let's just say this stack is 100 feet tall. My radius is 125 feet. We use a known natural phenomenon called point discharge. Point discharge is very simply taking a sharp point, and that little ionizer on that stack will literally have probably 5,000 or more sharp points. And you take that sharp point and you put that sharp point, you immerse it in a high electrostatic field. And as I mentioned at the previous discussion point, in lightning, we have a very high field intensity. When you put sharp points in a high lightning electrical storm, it'll bleed off charge. It actually dissipates that charge force on it. That positive charge is dissipated. And by doing so, we have created, at least in this illustration, a little gray cloud. So see a little gray cloud kind of around our area of protection? What we're saying in there is in that gray cloud, we have lowered the charge in the air, the electrostatic fields. Why is that important? Because I mentioned a few minutes ago, if I am going to collect a lightning strike, I have to develop an upward streamer. How do we develop an upward streamer? You have to have charge in the area of 100 kV. So we're never going to let that gray ghost area around my zone ever develop 100 kV potential. I don't care what happens outside that zone. As you can see here, the tree, other buildings, the lightning rods, they're developing streamers. I don't want to develop a streamer from my area. And when they develop a streamer, they win the race. And when they win, they collect a strike, but yet I have not collected it. To my primary goal is I don't want to have lightning hitting my protected zone. You could grow the array or protection to cover those buildings by applying more systems, more ionizer. But in this particular case, we were only worried about the stack. So very simply, what this technology does is it prevents collection by preventing streamers, by controlling the electrostatic environment in the area concerned. So here's an example of what that array looked like on that stack. It's kind of hard to see right here, but that might be about a 10-foot diameter stack. And we literally, in this case, have like 8,000 sharp points, and that's the ionizer, and that's what bleeds off that charge and controls the electrostatic fields below the level of streamer generation. Here you might be able to see in the left-hand illustration, this is over at SWD site in Texas, but you see all the sharp points up there? Greg, if you can kind of point up to that maybe, your pointer. Yeah, right up there, all the sharp points. Those are the points we're talking about. Literally, there's thousands of them in our system. Now, this is a very technical design. They're custom designed to make sure they have enough points at the right location to control the environment so we don't collect. This is PPG chemicals. You can put them on chemical plants, refineries, paper mills, power plants. ExxonMobil, here we have them on the process towers. You can see them on these little vent stacks, also on those process towers. Each one of those little arrays has thousands of points on them. One of our biggest customers, FedEx. We're protecting well over 2 square kilometers, approaching 3 square kilometers with our technology. We have 200 plus aircraft gates protected with this technology. We just ran some quick evaluation here, basically on strikes prevented. And the lower left-hand corner, you can kind of see some of the example of strikes we prevented over many, many years. And for example, at Federal Express, we have a 99% effective rate over a 20-year period, and PDVSA 100%. And you can see also just in the upper right-hand corner some of the Fortune 500 or Fortune 100 companies we've worked with, whether it be BASF, BP, Conoco, Pravanta, Huntsman, TNT, PPG, International Paper, you can kind of get a quick UPS, a flavor of who we've worked with. And I think we're pretty close to our time. Was the last slide, I think?
Yeah.
So is there any questions? If not, again, you can also send them to me as well, but I'll be available here now for a while, or you can also call us. And you have my number, Sean's email and my number. Well, again, I do encourage you to, number one, look at the YouTube video. I think you'll find it very informative. This is a very quick, really crib notes from that longer presentation. Secondly, you go to our website. We do have technical papers which you can access, which also goes to more technical side of what I discussed and who we are and what we can do. We'd love to give you some more ideas of how we can work with you. We all offer no obligation, no cost budgetary proposals for what our technology would cost for an application. And I think you'll find that when you look at our information, our website, our technical data, that we have a pretty impressive history and library when it comes to lightning protection and history.